Okay, students, welcome to video class 4, part 1, that is modeling of physical systems. So, before I'm going to say anything about modeling, I will just like to say something about the system. Just a recap of what you studied in signals and systems. Say, you can represent a system by a simple block diagram like this. Say that system is having an input, it is having an output y of t, and its impulse response is represented as h of t. Right. Now, we have studied that the transfer function of such a system is the Laplace transform of output to the Laplace transform of input with initial conditions is equal to 0. Okay, so this is the most important condition in the transfer function. This you should always keep in mind. The initial condition is equal to 0. Right. Okay, so this is a time domain representation of a time domain block diagram representation of the system. Now, the same system can be represented in frequency domain. That is, if you replace this x of t by capital X of s, and you replace this y of t by capital Y of s. So, what will be this transfer function? Transfer function will be capital H of s. So, you can replace this by H of s. So what is this? This is the time domain representation. Okay, while this block is the frequency domain representation of a system. Okay, representation of a system. Okay, now let's move on to this term, physical system. Physical systems are just primarily they are practical systems, and there are a lot of physical systems which are usually non-linear in nature. Okay, non-linear means the output of that system need not be always in a linear relationship with the input side, because that's a practical system. But what we usually do is we can represent this physical system by linear differential equation. Okay, differential linear differential equation. Okay, now for example, let's see, I will come to this point, linear differential equation. Let's see some of the examples. Now, what are the various physical systems that you can have? The two physical systems that you need to study, which is mentioned in your syllabus, is electrical and mechanical system. What do you mean by this? Electrical system and mechanical system. Electrical system are nothing but it is simply some circuits. It can be an RC circuit, it can be an RL circuit, or any other bigger circuits. I mean, an op-amp circuit. All comes under electrical system. While mechanical system can be, again, this mechanical system can be classified as translational system. That is, it is based on that displacement, or it can be rotational system. Okay, say for example, in an example translation system, it's a spring balance. Okay, so that motion is only in one direction, so that's why it is translation system. And in the case of a rotational system, say for example a gear system, or such things, or a stepper motor, all this comes under this, all motors, servo motors, all is having some, the armature is rotating, right? So there is a rotational motion. So such mechanical systems we call as the rotational systems. So all these are some of the examples of physical systems which can be represented by linear differential equation, but not that all these systems, practically all these systems, are non-linear in nature. So in a sense, this linear differential equation representation is not an apt one, but we can have for the initial analysis. Okay, but for a preliminary analysis and design, this linear differential equation is more than enough, and thereby it may restrict its operating range, because it is not, this any physical system is not strictly a linear system. There can be some amount of non-linearity. So when we represent such systems by linear differential equation, we assume that those systems, the non-linearity effect is minimal. So this set of differential equation, or this is a mathematical set of mathematical equations, right? And this set of mathematical equations of a physical system are called as the mathematical model of the system. Okay, mathematical model of the system. Now, why do you need model? Model is nothing but just to analyze that system, just to understand the dynamic, just to understand the dynamic behavior of the system. Now, what is the meaning of, I have explained it in signals and systems, right? Now, what is the meaning of this dynamic behavior? It is actually the change of the output with respect to the change of the input. So the changes, time to time changes, can be studied by this dynamic from the dynamic behavior, and that can be well explained by such mathematical model, even though this mathematical model is not perfectly apt for a physical system because of the non-linearity issue. But when we represent, for the meantime, or under this under the scope of your syllabus, we'll be restricting our study or towards assuming that all the physical systems are linear in nature, or in other words, the non-linearity issues in such systems are minimized. So we are free to represent this physical system by using linear differential equation. So this is the mathematical model. Now, using this mathematical model, you can also have another model called as a block diagram representation. That is also a representation, right? Now, imagine, just for an example, this is a simple system with the output and input with the impulse response. And what is this? This one is the block diagram representation of this. So actually, from where did you get this? From where did you get this HFS? Actually, you got this from y of t is equal to, right, h of t star x of t. Do you remember the thing which I taught you in signals and systems? This equation is an equation valid only for LTI system, linear time invariant system. And what is going to be our assumption? All the systems that we are going to deal is a linear time invariant system. That means this equation is valid for all the systems that we study. Okay, even though there can be some amount of non-linearity. That's what I emphasize that point. We will be considering, even though we consider various physical systems, we'll consider, or we will assume that the non-linearity issues is minimal, so thereby you can use this expression. Now, from where did you get this expression? That is, y of s is equal to h of s into x of s. Now, what happens when you apply Laplace transform to this? You know, from convolution property, okay, applying convolution property of Laplace transform, you can write this equation as y of s is equal to h of s into x of s, right? Or what is your h of s? H of s is y of s by x of s, under the assumption that initial condition is 0. Okay, and this approach, this sort of approach where we find the transfer function, is also called as the transfer function approach. I will be dealing this in the next module, in the coming modules, so that you will have a deeper insight into the transfer function approach. For the meantime, let's forget that. So this is it. This is how you got this equation, right? And from this equation you have developed a block diagram. Okay, so similarly, if you have a mathematical model or a differential equation, as you were studied in signals and systems, you know how to solve a differential equation using Laplace transform. Now, applying Laplace transform and assuming initial conditions to 0, you can find out the ratio between the output and the input, and that is what is called as a transfer function. Once you get this input, once you get this, right, you can represent this equation as this block diagram. So you can convert any mathematical model by suitably applying the Laplace transform. You can convert this mathematical model into a block diagram model. Okay, so these are the two things, these are the two models that we will be dealing under this topic. And there is one more model, as I mentioned earlier, that is SFG. Okay, that will be treated as a separate section. Okay. Okay, now let's move on to the next topic, which is the modeling of electrical system. Now, what is basically an electrical system? Now, from your network theory, from the knowledge of network theory, you can understand that electrical networks are basically a combination of resistance, inductance, and capacitance. Okay, now you can also have the active devices like diode, transistor, and all those things here. So we'll always start from the scratch, and so hopefully let's see. Let us concentrate on these RLC circuits. So these are all electrical systems. Now, once if you have an electrical system or a circuit like this, what you can do is there are two major laws associated with the electrical circuits or networks, that is KVL and KCL. Okay, using these laws, you can develop what? Using these two, you can develop a set of equations, right? Develop a set of linear equations or linear differential equation. Okay, linear equation or linear, precisely we will be employing linear differential equation. Okay, okay, right? Say for example, if you consider a RC network like this, say give V of t, this is RC. Okay, so how will you write this equation? This is equal to V of t equals, say current, assume that a current I of t flows, so this is equal to I of t into R, that is you're applying KVL plus what is this, 1 by C integral I of t dt. This is the voltage drop across the capacitor for a time function, right? 1 by C integral I of t dt. Okay, so this is a type of differential equation, and if you differentiate throughout, you will be getting the differential equation corresponding to this. That's what I told you. So using this KVL or KCL, you can develop what? You can develop a set of equations, and this equation we call as the mathematical model of this RC network, right? So similarly, if you have any electrical networks given, you can apply KVL or KCL as is suitable and develop certain set of linear equations, and you can have the analysis. So from the differential equation, now what's the next step? To get the model, what you need to do is transform this. This is a time domain equation, right? Now, how will you transform this to frequency domain? Now, you can transform this to frequency domain by what? By applying Laplace transform through that. Now, you can apply Laplace transform, all the time domain function, assuming that the Laplace transform V of t is equal to capital V of s, right? And Laplace transform of I of t is equal to capital I of s. So assuming that, you can convert this time domain. This is a time domain, right? Now you can convert this into frequency domain as capital V of s is equal to I of s into R. Okay, if you don't know, please refer my earlier signals and systems notebook. 1 by Cs into, okay, into I of s plus I inverse of 0. What is the meaning of I inverse of 0? I inverse of 0 is nothing but it is integral I of t dt. After integrating, put the result t is equal to 0, that is I inverse 0. Now, had it been some derivative, what will be this? If there would have been something like di of t by dt, suppose if that equation is having di of t by dt, what is the corresponding Laplace transform? This will be s into I of s minus small I of 0. What is the meaning of this? This is the I of t at t is equal to 0. Okay. Now, anyway, what is the intention behind this developing this transform? You need to get a relationship between the input and the output, right? So I'll explain this later when we do some examples. Just using this expression, for the meantime, you just believe that using this expression you can find out. Suppose, see, this is, let us call this as Vi, and the output across the capacitor as Vo. You can also write the equation for V out, right? From that we'll be able to get V0 of s by Vi of s, but initial conditions to 0. Now, when you consider the initial conditions to 0, this automatically becomes 0. That means making the equation a bit simpler. So you will be getting an expression to that. And what is this? This is the transfer function. So from the given mathematical model, you can arrive at the transfer function. Okay, is it clear? Okay, now once you got this transfer function, you can simply develop into a simple block diagram with Vi of s and V0 of s, and inside you can write your transfer function. Okay, this is the simplest way of representing the simplest block diagram, and I will show you that this block diagram, the inside of this block diagram can also be expanded, and I will show you how it is. Okay, that is actually the real block diagram representation. It is the generalized way of representing, just by representing a block, and inside the block you write the whole transfer function of this. That won't give you too much idea about that system. Okay, I will explain when we do some examples. Okay, so here is example 1, and the question is, you're given with a simple RC circuit. You're asked to obtain the mathematical model. Now you know what is a mathematical model. Mathematical model refers to set of equations not in the time domain. Yeah, I mean, that can also be called as a mathematical model. What it actually means is you will have to convert it into frequency domain. Okay, now then, and you are asked to find out, by using this mathematical model, you are asked to find out the transfer function of the system of this electrical network. And from the transfer function, or from this mathematical model, or the set of equations, or from the transformed equation, or that's a mathematical model, obtain the block diagram. So there are three things that you need to do. First is the mathematical model, then you need to find out the transfer function, and finally obtain the block diagram. Okay, now let us have a closer look at this network. Now this network is a network consisting of a symbol R and a C, right? Resistance and capacitance, and you are giving the input, let this small letter Vi of t, that is the input voltage, and the output you are taking across the capacitor, that is denoted by small letter V naught of t, right? So if this is the output and this is the input, what is the Laplace, what is the transfer function that you want? The transfer function, what you need to find out is capital V0 of s by capital Vi of s, right? Now, in order to get this, you need an equation that relates with Vi and V naught of s. But unfortunately, there is nothing like Vi of s or V0 of s here. So what you need to do is, you need to have the mathematical time domain equations. Now, how will you do that? So when a voltage like this is applied, you know that in a closed path, a current flows, and let us denote that current as I of t. Okay, now, right, so applying KVL, now when you apply KVL, what is the equation that you get? When you apply KVL, so this is small letter Vi of t is equal to this I of t into R, I of t into R, plus the capacitor, this same current flows through the capacitor, so that develops a voltage across the capacitance in terms of that time domain function, current function, as 1 pi c integral I of t dt, since c is given. Otherwise, if suppose it would have been some reactance, we just multiply the multiplying I of t into that reactance is enough. Okay, but this is c is given, so this is your time domain differential equation. I told you earlier that this can also be considered as a differential equation. If you differentiate it, this becomes dy by dt, di of t by dt into r plus 1 by c. When you differentiate that, this becomes I of t. So that equation becomes a differential equation. Okay, anyway, this can also represent a differential equation. Okay, now how will you get this? We need a similar equation relating vi of s and v naught of s. So for that, what we do is we apply Laplace transform. Now call this as equation 1, applying Laplace transform throughout 1, right? Throughout 1. So before doing that, you need to assume that the Laplace transform of vi of t is equal to capital Vi of s, and the Laplace transform of the next function we have is I of t. Laplace transform I of t is equal to I of s, right? Okay, now let's see how to write this equation. So when you write this, when you apply this Laplace transform, you can write this as Vi of s is equal to I of s into r plus, right, 1 by cs into I of s plus I inverse of 0. I have explained earlier what is the relevance of I inverse of 0. But anyway, we know that the whole model is to find out this ratio, or we call as the transfer function, and the condition is the initial condition equal to 0. So straight away you can put this is equal to 0. That means you can rewrite this expression as I of s into r plus 1 by cs into I of s. Okay, so this is Vi of s, and let us call this equation as equation number 2, right? Now let's see one again. Can you write the equation for v0 of t? Now what is v0 of t? V0 of t is the voltage that develops across the capacitors, right? Now we know that the voltage that across the capacitance will be integral by e of t dt into 1 by c. So you can have the write the expression for v naught of s. Now what is v naught of s? Right, let's start with the v0 of t. v0 of t is 1 by c integral I of t dt, right? Now what will be v0 of s? When you apply Laplace transform, you will get this as 1 by cs into integral I of s. I'm not going to write again this one. The explanation is the same. So this is v0 of s is equal to 1 by cs into I of s, and I'm calling this equation as equation 3. Okay, now the next step is what happens when you divide. Now we have got two equations, vi of s and v0 of s, and what is the transfer function? Transfer function is the ratio of that, and not only that, this condition is also met by substituting 0 for all the initial conditions. So writing that v0 of s by vi of s is equal to, this is how it goes, 1 by cs into I of s divided by what is vi of s? Vi of s will be I of s into r plus 1 by cs, right? This is it. Here I am taking I of s common, so that this becomes 1 by cs into I of s into this. I of s and I of s will get cancelled, so you can rewrite this expression as 1 by cs into r plus 1 by cs, right? So, or in other sense, this is 1 by 1 plus rcs, cs into r, and the cs, this gets cancelled, so this becomes 1 by 1 plus rcs, right? 1 plus rcs. Okay, I'm just changing the order, that's all. So this becomes 1 by 1 plus rc. And what is this? this is actually your transfer function, right? This one is your transfer function, right? This is your transfer function. Now once if you have the transfer function, as I explained here, once you got the transfer function like this, you can represent that as a block diagram, right? So the block diagram will be like this. That is the simplest way of representing it as a block diagram, is like this. What will be writing like the here you will have vi of s, here you will be having v0 of s, and what you will write for in the inside, you will write the transfer function 1 by 1 plus rcs. Okay, now the problem with this is, this type of representation is, we are not actually getting the just we will only get the overall transfer function of the system. And for a beginner, sometimes you may feel that this is an open loop system, but actually this need not be, and this is not an open loop system, and I will prove it later. Okay, that's the problem with this type of simplified block diagram representation. Anyway, the simplified block diagram representation we will see later. Our aim will be, if you are given with a block diagram, our aim will be converting that big block diagram into this types, so that you can straight away you can read what is inside that block, and that will be your transfer function. Okay. Okay, now looking at this equation 2 and 3, this 2 and 3, I'll rewrite this 2 and 3. Okay, now from this equation, so I have rewritten this second equation again here. So this is vi of s is equal to r into I of s into 1 pi cs into I of s. So this is again KVL, right? This is an equation we got from KVL. The only difference is this is a frequency domain or S domain circuit. Now how will you draw the S domain circuit here? Okay, as usual, this starts from, right, vi of, okay, this is plus vi of s, right? It starts with vi of s, and you have a resistance R, and through this R, what happens? An I of s current flows, and that the same current also flows through a capacitor C, right? So I of s, so I of s into, so if this I of s into R, this is resistance, this 1 by cs has to represent what? Then only it will be giving you voltage. So if this section has to give a voltage, this 1 by cs has to be what? Has to be resistance, or we call as a reactance. Okay, so this is 1 by cs. Okay, you can straight away, you can recollect that. You just put, this is just a topic outside this, just for your information. What happens when s is equal to j omega? When you put s is equal to j omega, s becomes j omega c, right? Bringing this j upward, this will be minus j by omega c, right? This is how you, in your network classes, you have represented this as the reactance, and you simply multiply that. So that same thing we are doing in the frequency domain, that is, you're multiplying I of s into C of s. Now you may just rewrite this equation, and by applying KVL you will be getting the same equation. So from the given equation you will get a circuit. And what is this circuit called? This is actually the transformed circuit, or the circuit in S domain, right? In S domain, right? Now one more point is, what is this V0? Now what we know, that this is V0, right? Now this can be represented as V0 of S. So what will be V0 of S? That is a drop, 1 by Cs into, right, 1 by Cs into I of S. 1 by Cs into I of S is your V0 of S from this. So this is your third equation. So, right, this is the third equation, right? This is how you obtain this, right? Okay, now, okay, what happens when you substitute 3 in 2? Now, 3 in 2, we'll get, this is Vi of s is equal to R into I of s plus V0, right? V0 of s. Now you can have a slight rearrangement. This is Vi of s divided by V0 of s by R is I of s, right? Okay. So the same I of s is flowing through this capacitance, right? So from this equation, from this one, you can write I of s as what? I of s is equal to Cs into V0 of s. This is V0 of s, right? So both these I of s are the same. So it is the same I of s that is flowing through R that we got this as by Vi of s. I mean, even if we just have a look at this, just logically, what is the voltage across here in terms of S domain? It is V0. This is Vi. What is the potential difference? This will be Vi minus V0 of S by R. So that is the current flowing through this. And the same current flows through this Cs. And what we do is we equate this. The same current flows so that now call this as equation 4 and this is equation 5. Equating, no, so you hope you understood why I am equating 4 and equation 5, because both represents I of s. Now when you equate that, what you get is Vi of s minus V0 of s by R is equal to Cs times V0 of s, right? Okay. Now, okay, fine. V0 of s minus V0 of s by R is equal to Cs into V0 of s. Now, from this equation, we can write this V of s minus V0 of s is equal to RCS into V0 of s. Okay. Now, this is the equation. To call this as equation 6. From 6, we are going to develop a block diagram. Okay, develop a block diagram. So as I told you earlier, this is the simplest way of representing this block diagram. What is the problem with this? You will get a feeling, especially for a beginner like you will get a feeling that it is a open loop system, but it is not actually open loop system. There are various blocks inside this block, and that's what I am going to find out. Now looking this equation, can you write the block diagram? So anyway, you know the two inputs. So this is how from an equation to develop a block diagram. You must attend it very carefully. I'll do one more example. Don't worry if you don't get this. So you have Vi of s and mark this as V0 of s. These are the two ends. In the left hand, you just denote the input side and the output side as V0 of s. Okay. Now, what does this equation shows? That is, this equation shows that Vi of s minus V0 of s. Now, if I want the signal V0 has to be combined with Vi of 0, right? That is, Vi of s has to be subtracted. No, V0 of s has to be subtracted from Vi of s. That is this equation says. So that means here you have Vi's, here you have V out of s. Okay, in between, assume that there is something. We do not know what it is. Okay, anyway, at the output, you know it is Vi of s. But this equation shows that there is a subtraction happening, or a comparison, or a summing happening in the form of Vi and V0. So if this operation has to take place, this has to come to this side, or this has to come to this side. Okay, anyway, it is customary to represent like this, right? So this can be represented. So this is the whole of V of s, right? Vi of s minus the whole of Vi of s. So I'm calling this as 1 because you need the whole of this. And what you do is you are having a summer. Here you have a plus sign, here you have a negative sign. So what is the result of this? The result here will be what? This will be Vi of s minus V0 of s, right? Okay. Now, this must be equal to RCS times V0. We have the V0 here. We don't want this RCS. So, this RCS has to be brought here, right? Right? So I'll rewrite that equation. So here you have Vi of S. So what is Vi of S minus V0 of S? This is to be, now we have V0 of S. So this and this are to be connected. How will you connect that? Now from this equation, from equation 6, you can write this V0 of S as this difference divided by RCS. Right? Okay. So that means this particular thing has to be multiplied by what? 1 by RCS. So if you have a block like this, inside that if you have 1 by RCS, what will happen? This Vi of S minus V0 of S, it gets multiplied by this, forming this, and that is your V0 of S, so that you can connect this. Right. So this is actually your real block diagram of this network. So now you judge, is it an open loop system or a closed loop system? This is a closed loop system. And what is the specialty of the closed loop system? What is the H of S here? H of S here is, okay, H of S is equal to 1, right? What is G of S here? That is a forward path gain. It is 1 by RCS. Now use your equation. C of S by R of S. What is that? And this is a negative feedback system. That is GS by 1 plus GSHS. Just substitute. And you are going to arrive at this answer, right? Okay, you do this by yourself. Just substitute 1 by RCS and 1 in place of this HFS, and you can, surprisingly, you will be getting this answer 1 by 1 plus RCS, proving that this is actually the transfer function. And not only that, this is not an open loop system, this is a closed loop system. And one more speciality I want to notice, just study it from now on itself, that is, what is the speciality? There is no gain. I mean, the gain is actually 1. That is in the feedback path, the gain is equal to 1. Such a system with unity gain is called as a unity feedback system. Okay, unity feedback system. So from hereafter, if you are given with a block diagram and saying that this is a unity feedback system, the first thing you will be getting a data will be H of S is equal to 1. So that can simplify many of your problems if a unity feedback system is considered. Hope you understood how to convert an equation into a block diagram. Okay.